Okay guys, so we are at the end of the controllability and observability, and we know that if the system is completely state controllable, means we can control the states to push them to desirable set points that I'm going to teach today. And if because of any reason we cannot measure the state vectors because of the inaccuracy in the sensors or because of the noise, so we're gonna use observability property to estimate those state variables. Okay, so now let me summarize everything until that we have done today. You have to know this. Okay, if you have a LTI system, linear time invariant system of x dot is equal to ax plus bu, and system is CISO, single input and single output here. Okay, and the y, the output is cx plus du, is right, huh? So, and this is the output. So, and for this LTI system, I told you that the solution of this is gonna be x of t, and this is n by n matrix A, this is n by 1, this is n by 1, and because the system is CISO, we have only one input. Okay, single input. This is a scalar, this is a scalar here for the CISO system, and this is n by n. That's right. So x of t is EAT that we named as, I'm summarizing everything, at the state vector at time 0 or initial time, from 0 to t, if you remember, exponential of a t minus tau and b u of tau d tau, and we name this as the matrix exponential that we know that EAT matrix exponential we can calculate from the Laplace inverse of SI minus A inverse. Okay, or from, if you remember, Sylvester determinant. That's right, if you remember. Huh? And then we came to the state controllability, controlability. So I said that if you want to check the complete state controllability, you have to check this controllability matrix that is from here b a square b until what? A n minus 1 to power of n minus 1 in b, and I name it m. So if the system rank, if the rank of this m is n, or because we in this course the majority of them they are the square a, okay, or its determinant of the m is not 0, m is not 0 means non-singular, so your system is completely state controllable. And then we came to observability, we came to output controllability, okay. So you have to check this matrix, CB, from left you multiplying by C, CAB, CA2B, and CAN minus 1B. So you have to check again the singularity or non-singularity of this number. Then comes to state complete observability, state observability. So you have to check this matrix. Let me do that here. This matrix, C, CA, CA square, CN, C, and CA n minus 1, as you have in your notes. Again, the rank of this matrix, this, if I say n, must be n. Understand? We have to check. Or determinant of the m where the a is a square must be non-singular. Because it is not a square like a robotic systems. We have to go to the pseudo inverse, and this is too complex. So in this course, we assume that the A is a square matrix. Okay. So these metrics, controllability matrix, observability matrix, and the output controllability matrix. You have to check these. This is the summary of whatever I have taught until this point. But when I'm talking about the state controllability, means I can control a state of the system. The state of the system can be pressure, time derivative of the pressure, temperature, time derivative of the temperature of a room, position of your car, velocity of your car, name it, whatever. Okay, I can use a controller U to push them to a desirable position or desirable set point. Simply, suppose that you have an AC in your a chiller in your room. Okay, so you want, and the room temperature is currently I don't know, 95 Fahrenheit. That's right. But you're gonna cook inside the room for a long period. So you need a controller U, okay, that brings down the temperature to 70 Fahrenheit. So we name it as set point. Set point. This is our set point. We want this. This is desirable. Desirable, like as undergraduate control. Okay, desirable set point. So we are designing this in this course for this LTI system. For this LTI system, how to design that. So what is this state variable of your room temperature? Is T temperature and T dot. Means rate of the temperature. Understand? So this is your X state vector. Okay, understand? Or if you want to, I don't know, for example, if you have a tank of the water, okay, it's a tank of the water, okay, and the current pressure is, for example, they are just numbers, okay, ballpark numbers. I don't know, say, stupid number, 100 megapascal, okay, funny number. But you want to bring down to, I don't know, by some pumps and the pipes and whatever, you want to bring down to 25 megapascal. Like as the air. So this is your set point. This is set point. This is desirable set point. So you need a controller U that you'll learn here how to design it to do that. So the state vector of your system is what? For this tank is pressure and the rate of the pressure with respect to time, P dot. Okay, understand? So this is the whole history. So we started controllability because we want to design a controller to push our system state variables to desirable set points. Or we want to design again a controller, we say the dual property. I'm going to teach you that estimate that unknown state vectors because of the noise, because of inaccuracy in sensors. Okay, so we're gonna go there from today. Okay, now, so how we do that? Let's start with the controllability. Let me start with the push the state vectors to the desirable set points. The name of that in the literature is pole placement. Pole placement. Okay, why we name it pole placement? This backs on the graduate control. Remember, if this is y over u, output over input, suppose here is 1 1, this is s square minus 2s plus 1. This, you have such a system from undergraduate control. The roots of this denominator, that characteristic equation, we name characteristic equation. Okay, are the poles. That's right, poles of the system. So here, here we are not blind that if you say minus s square minus 2s plus 1 is 0 from on the kindergarten level mathematics, you know have this from algebra. That's right. So you have two poles, P1 and P2, two repeated poles. They are plus 1 and plus 1. That's right. And if you remember from undergraduate control, you know that if you have such positive poles, if I plot in the S-plane, for those of you that you forgot, this is imaginary axis, this is real axis. We know that this area is area of the instability. This area, left hand side of the imaginary axis, is the area of instability or unstable area. Unstable area means your system gonna lose stability. That's right. But this side, right hand side of the imaginary axis, is stable. That's right, from undergraduate control, stable. That's right. And what happens about the imaginary axis? Remember from vibration course I was teaching. Oh, let me change the color, make it blue. So from vibration course and undergraduate control course, so if your poles are located at this, we were naming this as what marginally stable on the imaginary axis. If you have a pair of j omega like this, if you have pair of complex poles P1 and P2 here on the imaginary axis, so you're gonna have marginal stable system. If you remember from the vibration, marginal stable system gonna oscillate forever, like as the pendulum. That's right. Right. So now in this system that I'm saying, you have two poles. It is plus 1 and the plus 1. So your system is unstable, whatever it is. It is the car, it is a single degree of freedom robot, whatever. I don't care. Okay. So your system is unstable. So you have to place the pole. You have to design a controller U through this LTI system. X dot is equal to AX plus BU to move this pole to right hand side. Okay, understand? To the right hand side. So that's why we name it pole placement. Okay. So we have conditions for the pole placement or designing controller for these LTI systems. LTI systems. Okay, and I'm gonna teach you mathematics. Then I will go to what? To MATLAB. Okay. First is that all state variables means X. That's right. Are measurable for feedback. Okay, understand? And you know what's feedback from the graduate control. I'm going to teach you just in block diagram. This is first, so we can measure all the state variables to put in the feedback loop. That's right. Second is, if the system is, let me change the color because I taught you this and now you know the application of that, is completely state controllable means that you have to check what? You have to check the rank of this matrix B, A, B, A square B until A n minus 1B. You have to check the rank of this matrix. Is completely state controllable do it black. The poles, okay, of the closed loop, you know this term from undergraduate control, right? Closed loop system may be placed, pole placement at any desirable, I'm putting on the line because I taught you, for example, for the room, your system is desirable state vector is 75 Fahrenheit in temperature. Desirable locations. Why I say locations and I emphasize locations. If your poles of the system, okay, or state of the system is located in the left hand side, your system sucks, is unstable. You have to put in the desirable right hand side of this locations. Understand? Locations, let me go. Locations to next page. So if the system is completely state controllable, the poles of the closed loop system may be placed at any desirable locations. Next page. By means of I'm changing the color because it's very important. By means of state, this is the controller that you're going to do in this course. State feedback with the aid of gain metrics. So in this course you're gonna design controller using this formula. I'm gonna teach you mathematically state feedback and tuning the gain. Okay, so this is how we design controller in this course. Okay, let me see. Okay, now for making everything simple, we assume control input u of t and u that you're going to design by state feedback, and output signal y of t from here. Get here, because system is LTI and CISO. This and here we go. This, okay. Y of t to be scalars. They are numbers, single numbers, because your system is CISO, single input. Your system is CISO. Here I'm teaching. I will extend that to the MIMO, multi input and multi. I will extend this to MIMO, but here I'm going to teach you CISO, single input, single output. Okay, so example, you want to have this output for a second order system. This is example. The output only is the position of the car, or let me write in this format, is only temperature of the room, or it is pressure of the tank, or whatever. Okay, or sometimes you want to have this rate of pressure of the tank. This is the output that you wanna control. Okay, So another assumption is, for simplicity of the teaching only, the reference or desirable, this is that what you want to have, desirable input, like what? Like this 70 degree that you want to have, 20 megapascal you want to have, okay? Desirable reference desirable input is 0. What does it mean? Guys, look at here. Remember the phase portrait I plotted for you? I'm saying this is the phase portrait, the velocity versus position, okay? So suppose that starting from any initial point, the desirable reference input at the end, you want to go back here. You want to go back here to the 0 and 0. Or you start from here, you want to go here again. Okay, here we go. So we assume that the things that we want to achieve the origin as desirable set point. You want to go to 0, and you're gonna tell me, hey professor, you told us that you want to keep the temperature of the room to 75 degrees. Yeah, but you can change the parameter, huh? Well, for example, this is x of desirable, yet I want to keep it at 75 degrees. So now I can say I define a new reference input, which is x of d minus 75 degrees. Do you care? So whenever, so this is that you want to do. You want to do that. Understand? So because this is how much? 0. Just put it here. So you can transfer everything to the origin. Simple like that. Okay? Oh, yes. Okay, so these are things that you have to know. Now, having this, the necessary and sufficient condition that the closed loop poles of the system can be, again, when I say placed, means I want to move from the left hand side to the right hand side, can be placed at any, I say, desirable locations in, I'm changing the color because I just taught you, in the S-plane, means here, where I plotted that. This is face, this is S-plane, that's right. This is S-plane. This is S-plane. Huh? In the S-plane, is that the system must be, guess what? Must be, yes, completely what? State what? Controllable. Here we go. Now you know the controllability matrix advantage. That's right. If your system is not completely state controllable, meaning that the rank of the controllability matrix is not n for the nth order system, or is square, controllability matrix has zero determinant, is singular, okay, your system cannot be, the poles of the system cannot be placed at desirable points. So you as control engineer, first for the LTI systems, you have to check the controllability matrix. If it is non-singular or its rank for the nth order system is n, then you can proceed using the state feedback that I'm going to teach you and the gain matrix to design controller. Clear? So now let us go to slowly to design of design by pole placement, designing of the controller. So designing of controller means what? Here for sister system, a scalar u. Okay, u by what? Pole placement approach. Here we go. If you remember in the undergraduate control and the vibration course that you had with me, ME 520, I taught you, we remember that we wish to, in undergraduate control, to design a compensator or controller to have what? Do you remember in undergraduate control vibration? To have desirable, if you remember, yeah, damping ratio, remember? Damping ratio, zeta in the vibration undergraduate control, and natural frequency in omega n. Why we want to have? Because in undergraduate control, I taught you in the vibration course, I taught you that in most of the system you want to have a pair of complex conjugate poles. I said in the most of systems, like as your car suspension system, after passing a bump, you want to have under-damped response. Under-damped response means that you want to have a desirable poles of a complex conjugate poles minus zeta omega n plus I omega n 1 minus zeta square. Remember that we named this a damped natural frequency omega d. So you want to have a pair of complex conjugate poles for your car suspension system, that's right, and many other systems. Okay, So on the graduate control, we want to have the damping ratio of the zeta and natural frequency. Obviously, when I'm talking about the robotics, do you want to have under damp system, meaning that the zeta is smaller than 1? Do you want to have that? No, because if you have that, if you have under damp system, at the end of the day, the end effector of the robot gonna oscillate and gonna hit the object. So for example, for robotics, we want to have zeta of 1. Okay, zeta is greater than 1 is not good because this is over damped system. So we want to have the critically damped system, for example, for robotics. Critically damped system. We don't want to have any transient oscillation even. Okay, but this is for the over damped system that is very slow. Okay, so this is undergraduate control. But now here we're gonna use that pole placement to push the system states X to desirable position. Sorry guys, God bless me. Understand? Okay, now let me gradually introduce that for you. Okay. Go on. Okay, so as I said, pole placement specifies all closed loop poles, okay, and placing all closed loop poles requires measurement of all state variables using a state what? Come on, I taught you. State observer. So observer is estimating, that's right. Measuring. Observer. As in the system. So you see that controllability and observability. Controllability means pushing the system to desirable position, and but needs observer to measure or estimate. So they are coupled problems. Okay, so controllability and observability, they are coupled problems. Observability, they are coupled. Okay, I'm going to teach you mathematically. Okay, clear? See. Okay, so now let's go to mathematics. Yeah, we have this LTI system. X dot is equal to AX plus BU, and the Y is equal to CX. Now I'm teaching you pole placement, control part of that, not observer part of that, plus DU, where X is the state vector, as you know, and now you know, N vector. Okay, you have N state variable. Y is output signal that you want to control or whatever you want to do. And as I told you, it's a scalar here. Scalar is not just a single number. U, like a Y, as I told you, it is control signal that you're gonna design as controller and implement the Y experiment. Also, this is scalar because I'm talking now about SISO system, single input, single output system. Okay. A is n by n for nth order system is constant matrix because this is linear time invariant. Okay, constant matrix. B is n by 1, also is constant matrix. C is 1 by n, again is constant matrix. And the D is constant number that we see here that we assume 0. This is scalar again because U is a scalar. Okay, and by having that, I'm just introducing, oh, come on. Okay, by having these, and now I define the most important topic of this course as a basis of our future efforts is state feedback. State feedback controller. Okay, and we're gonna stick to this. I'm gonna expand this through the semester. So state feedback is this. U is minus K, this is gain matrix I was talking about, X state variables. Okay, so this is state feedback. This is state feedback controller, this is controller, this is controller. We just designed the controller. State feedback means that the control signal is determined by an instantaneous state. Bingo. What does it mean? First of all, as I told you, K is what? K is gain matrix. In the state feedback, our function is to determine gain matrix. This is the whole things that even that teach you LQR controller by using a state feedback, you have to determine this K matrix. And the X is the vector of the state vector. What is that? Say in x1, x2 to xn. Here we go. Understand? So if I expand that, so U is K1, K2, Kn in x1, x2, xn. So you're gonna determine this until this. That's right. This is 1 by n. This is n by 1, and the result is 1 by 1, a scalar, as I taught you. This is the whole history of this course. Now we're gonna expand this. We're gonna make it optimized by LQR controller. We're gonna go there 1 by 1. So the name of this controller is a state feedback controller. Okay. So K is the state feedback gain matrix. So K is state feedback gain matrix. State feedback gain matrix. Okay, and the K is 1 by n matrix. Okay, so I have to go to this mathematics, so I'm going to do it in the next class. So today I try to teach you whatever I taught in summary from page 1. See? Oh, there we go. What is that? Yeah, here we go. Come on. Oh, here we go. So this is what I taught you the state controllability, state observability, output controllability, and how they works, and the LTI system is solution metrics exponential, and then came down to remind you too many things about the S-plane, imaginary real, and the pole placement, and too many things, and the conditions that we can place poles on the system, what is state feedback, gain metrics, and we are going on. Okay, and we said that desirable things that we want to control is origin. You got it? So I'm going to continue with the next class, and we are going to determine this by deep mathematics.